Welcome back, ladies and gentlemen. Today we're discussing the free vibration of damped and undamped single degree of freedom systems. We're gonna start off today with the undamped equation of motion that we discussed in the last lecture. So our undamped equation of motion was the following. We had the inertial component, which is mass times acceleration, plus stiffness times displacement is equal to 0. Now, this is a second order differential equation, and the general solution to this differential equation is the following. U is equal to A1 cosine omega nt. As you recall from the last lecture, omega n is the natural frequency. It is the undamped natural frequency, plus A2 sine omega nt. Alright, so we're suggesting that the following equation is the solution to the differential equation that constitutes the undamped equation of motion. Alright, so how do we test this hypothesis? How do we make sure it's correct? The simple answer is we have the equation for u. We can take derivatives a couple times, find the equation for u dot dot, plug it in back into this equation, and realize whether it equals to 0 or not. So let's try that. To begin with, we want to start off with u dot, and taking derivatives with reference to time gives us the following. We have a1, the omega n comes out of that cosine, sine omega nt, and the second term gives us a2 omega n cosine omega nt. Alright, now we can do the same thing for the second derivative for the acceleration term. Okay, here it is. Now let's try and plug this equation and this equation back into our undamped equation of motion. Let's see. We have our minus a1 omega n squared m cosine omega nt minus a2 Okay, that is the second term. There are two more terms. We have an a1k cosine omega nt plus a2k sine omega nt. And this whole setup equals to 0. Now, what we want to do is to collect all the cosine and sine terms and see where we can go from there. So what we're going to get is brackets minus a1 omega n squared plus a1k cosine omega nt minus a2 omega n squared mass minus a2k sine omega nt is equal to 0. Alright, now what is the implication of what we're seeing here? We know for a fact that, oh, by the way, we forgot one term here. There is supposed to be a mass term here. Okay, so the implication of this is that omega n squared times mass gives us k. minus a1k plus a1k, that whole thing is equal to 0. Same thing with the second bracket. This term here is k, so we're going to end up with a2k minus a2k is equal to 0. Alright, so this is an indication that the solution we've provided for this undamped equation of motion is in fact true, and we're going to proceed by introducing some boundary conditions now. Usually, anytime we have a dynamical system, this dynamical system comes with some sort of initial condition. So let's call these initial conditions. And with initial conditions, what it really means is at time 0, we have some sort of position, some sort of displacement, and we can call it u naught. And at the same time, we can have some sort of initial velocity. We call it v naught. And so the next thing I could do is to take this homogeneous solution that I had for this second order differential equation and plug in my initial conditions. The first component of the initial condition is the time. The time is 0. So I want to say u0, that's from the first equation, is equal to a1 cosine 0 plus, and then I have the second term, a2 sine 0 is equal to u naught. And because sine 0 is equal to 0 and cosine 0 is equal to 1, I have the following scenario. A1 in this case is going to equal to u naught. Okay, great. Now we have a second initial condition involving the velocity, and to take care of that, I want to go and look at my this second equation here in the middle, describing the velocity term, and what I have is the following. I have u dot 0 is equal to minus a1 omega n sine 0 plus a2 omega n cosine 0 is equal to v naught. So again, sine zeros are equal to 0, so this first term is goes to 0, and cosine zeros are equal to 1. And if I do the math correctly, I should have v naught divided by omega n. Alright, so that's our first term here, and this is our second term. So the general solution to the undamped equation of motion can now be written as follows. So let's choose a different color. We're going to call this the general solution. Ut, because displacement here is a function of time, it develops with time, is equal to u naught cosine omega nt plus v naught divided by omega n sine omega nt. And this is really our general solution, and this general solution was for the undamped case. Now what if we have damping? So we're interested in the damped equation of motion, and in that equation, if you recall, we had a damping coefficient and the velocity term. So let's see, we have our inertial component mass times acceleration plus damping coefficient times velocity plus stiffness times displacement is equal to 0. Another reason why this lecture is called free response has to do with the fact that we're not imposing any kind of excitation or any kind of forces on our structural systems. We're merely dealing with initial conditions that involve initial velocities and displacements. And so if I gave you a case like this, what I could do is to divide this whole equation by the mass term. So I'll have and when I divide stiffness by mass, I get omega n squared. And the omega n squared was our natural frequency squared, and that's really a fundamental relationship that we need to be aware of. Now, here's a new relationship for you to remember. The damping coefficient is equal to 2 times mass omega n times a new parameter we're going to call zeta. This zeta parameter we refer to as damping ratio. And this damping ratio is not to be confused with damping coefficient. In fact, this damping ratio is unitless, whereas the damping coefficient has units. Alright, so now what does this damping ratio mean? To do that, I need to first draw a plot. Let's see, let's draw one of these plots. Let's say I have a dynamical system which develops over time. So I have ut on the vertical axis and I have t on the horizontal axis. And I'm given some sort of initial condition. What happens is that whenever I am given a damping ratio that is less than 1, less than the value of 1, we call this the underdamped case or the underdamped response. What happens is that our structure will oscillate itself and the response slowly reduces until it goes back to 0. But what's really key here is the oscillation. Even though we are following an envelope that's taking us back to 0, now this is our envelope, we still have to be aware of the oscillation that's occurring. And this is really what most structural systems experience. Most systems tend to be underdamped. Now, what happens if zeta is equal to 1? For that, I'm going to choose a different color. I'll say, let's see, zeta is equal to 1. We call this the critically damped case. And whenever we are given a critically damped case, we typically start off at the same position, but this time we're no longer going to oscillate. And what happens is our structure is going to go to the 0 position, kind of like that, without any oscillation. Now, what if zeta is greater than 1? Okay, let's choose a different color. This time we're going to choose green. So zeta is greater than 1. Now, in such cases, we tend to go to the 0 position, but it may just take longer. So may follow a trajectory that kind of looks like that. So what's really important here is to remember that anytime we have an underdamped situation like we see in here, we're going to end up with oscillations. Okay, so what is the response for an underdamped system? So we're interested in the underdamped response. And underdamped we said was zeta is equal to, zeta is less than 1. Okay, so as it turns out, we're not going to do the proof in this lecture. You could probably do that on your own. The answer is the following. ut is equal to exponent minus zeta omega nt multiplied by, so this first term is an exponential term that kind of takes us on a trajectory that looks like that. And then we have the oscillation terms. So we have brackets open, u naught cosine omega dt. I'll explain in a second what omega d means. Plus v naught plus zeta omega n u naught. We're going to divide this by omega d sine omega dt. And we're going to close the brackets. And the second term, as we mentioned, is the oscillation term. So we can have a response that goes down, up and down, up and down. But at the same time, it has to follow this downwards trajectory to a zero position. So the question now is, what is omega d? Omega d is the damped natural frequency. And the damped natural frequency is equal to, omega d is equal to the undamped natural frequency multiplied by 1 minus zeta squared. And this holds true as long as zeta is less than 1. Okay. Now I could also give you the critically damped response. And for the critically damped response, we have a smaller equation that is going to equal to u naught plus v naught plus omega n u naught, closing the brackets. But there's a time term t, close the brackets again, and then e minus omega n t. Okay, so that's what we have, and the last thing I want to do is to do an example. And this example is a continuation of what we started in the last lecture. In the last lecture, we had this mass that was hung from some sort of very rigid ceiling, and this mass had a magnitude of m. It was hung by a spring element that looks kind of like that. It has k as its parameter, and there is also a dashpot element which we're going to call c, and it's also hung from the ceiling. And what we're going to use for measurement is the stretched position. If you recall, in the last lecture we talked about the unstretched position. This time it is the stretched position. That means that this stiffness parameter is already at the equilibrium with the gravitational pull. So that's really what we have. So u of t is from stretched position. So let's keep that in mind. And the parameters we have are k is equal to 1.2 newtons meter, m is equal to 0.8 kilograms, and zeta is equal to 0.1. So I can easily calculate my damping coefficients from what's available here. Firstly, I can get omega n, or my undamped natural frequency, from k divided by m square root. Then I can find my damping coefficient, which is 2m omega n zeta. And because zeta is less than 1, I am interested in the underdamped response. And that's what I'm going to do. So now I'm going to pull MATLAB open and show you what I've done on MATLAB. Let's see. Alright, this is what I have. I've plugged in my parameters. I've plugged in the initial conditions. Something I forgot to mention is that the initial condition for this question is the following. U naught is equal to 0.1 meter and V naught is equal to 0. You could play with that on your own. As long as we get the equation right, everything should be correct. And so we have the following situation. We're looking at the response, and lastly we're plotting. So let's run this. Okay, so this is what we're getting. We have our initial condition at time 0, and then we have a drop and oscillation, and then the response is damped out to a 0 position over time. Okay, so I hope you found this lecture useful. We looked at free vibration of damped and undamped systems. In the next couple lectures, we're going to focus on excitated structures. So we have different kinds of excitations. We have ramp forces, step forces, harmonic forces that we're going to look at, and hopefully you'll find those useful as well. Alright, leave any feedbacks, questions, comments in the comment section. I'll get back to you as soon as I can. Appreciate it.